We're absolutely drowning in data these days, right? But what if I told you that inside all that noise, the chaos of the stock market, the signals firing in our brains, there are hidden patterns, a secret rhythm. And today, we're going to learn how to actually listen to it. All right, so let's kick things off with a little puzzle for you. What on earth do earthquakes, stock prices, and our own brainwaves have in common? I mean, think about it. They seem totally, completely unrelated, right? Well, believe it or not, the answer is that they're all playing a kind of music. Yeah, you heard that right. Each one has this hidden rhythm, this secret song made up of underlying frequencies. And if we can just figure out how to isolate them, they tell us a really powerful story about how things really work. Okay, so that's the big idea. But how do we actually do it? How do we go from something that just looks like pure chaotic noise to hearing these distinct individual notes? Well, to pull that off, we need a special kind of tool. Think of it like a prism, but instead of splitting light, this one splits time. So normally we look at data the way it happens, right? Over time. You watch a stock price go up and down over a year. That's what we call the time domain. And sticking with our music analogy, it's like hearing a big complex chord played on a piano. Bam! You hear the whole thing at once, the full sound. But good luck trying to pick out every single note that makes up that chord. It's just a wall of sound. What we really need is a way to switch over to the frequency domain. We need to break that chord apart and see the individual notes to find those fundamental cycles that are actually building the whole thing.
And the magical tool, our prism for time, is called the Fourier Transform. It is, without a doubt, a mathematical marvel. It takes that jumbled, messy, time-based signal and poof! It just beautifully lays out all the individual sine and cosine waves it's made of. It's the thing that lets us finally stop hearing the chaos and start seeing the notes.
Okay, so now we've got our notes. Our Fourier transform has done its job. But now for the next crucial step. Which of these notes actually matter, right? Which ones are being played the loudest in our data's secret song?
And that's where something called spectral density comes into play. The best way to think about it is like a volume knob for every single frequency we found. It literally measures how much of the data's total power or variation comes from each specific cycle. So, if you see a high spectral density at a certain frequency, you know that's a really, really dominant, loud note in the melody. So how do we see all this? Well, we use a nifty little tool called a periodogram. This is our go-to way to get a quick map of the spectral density. Honestly, you can just think of it as the actual sheet music for our data. It's a simple graph that shows us, plain as day, which notes are hitting hard and which ones are just kind of humming in the background. And boom, a periodogram just makes the whole pattern jump right out at you. Like in this example here, you can see that middle frequency bar is way, way taller than the others. That's it. That's our dominant cycle. It's the recurring beat, the main melody, that was totally invisible when we were just staring at the raw data.
Now, this isn't just some abstract math problem, not at all. This technique has literally been used to uncover some of the most fundamental patterns in our world. It's like we've found the hidden playlist that's running in the background of, well, almost everything.
Let's take economics, for example. For decades, analysts have used spectral analysis to slice right through the daily noise of market chatter and cable news panic. By looking at long-term data on stuff like GDP and stock prices, they can spot these longer, much more meaningful rhythms. The classic boom and bust cycles that we see play out time and time again. And you know what one of the loudest notes they found is? A recurring cycle that pops up roughly every 10 years. Being able to spot that rhythm is a game changer. It helps economists understand and maybe even anticipate big market shifts way better than they ever could by just reacting to today's headlines. Or how about seismology? When an earthquake hits, it's not just one big shake. It's a release of energy across tons of different frequencies. By analyzing the spectral density of those seismic waves, scientists can really understand the character of the quake. And that knowledge, it directly feeds into how we design safer buildings and bridges that can actually withstand that kind of shaking. And you can bet environmental science relies on this stuff. It's absolutely indispensable. It's the tool that lets scientists sift through decades of messy temperature data and pull apart the really obvious cycle, summer, winter, from much longer, more subtle patterns like El Niño. It helps filter out the noise so we can get a much clearer picture of our changing climate. Now, this all sounds pretty amazing, right? But getting a perfectly clean recording of our data song, it's not always that simple.
Just like a music producer in a studio, there are some real challenges you have to tackle to get that perfect final mix. And probably the biggest challenge of all is something called the bias-variance trade-off. Here's the deal. If your analysis is too simple, that's called high bias, you basically miss the song entirely. It's like trying to hear a symphony with earplugs in. But on the other hand, if your analysis is too complex, that's high variance, you start overfitting. You start hearing notes that aren't actually there, mistaking random static for a real melody. The whole game is finding that perfect sweet spot right in the middle.
And luckily, just like a great sound engineer, we have some tricks up our sleeve to clean up the recording. One is called smoothing. It's basically like turning down the static on a radio. It averages out all that random jittery noise, so the true underlying melody can finally come through. Another cool trick is tapering. This helps prevent something called leakage. You know how sometimes a really loud bass drum can kind of drown out the guitar next to it? Tapering stops that from happening in our data, making sure every single note is crisp and clear on its own.
So, when you really think about it, from the economy to the Earth itself, spectral analysis gives us this incredible new lens to understand our world. It proves that underneath all the apparent chaos, there is so often a hidden, predictable order just waiting to be found. And that leaves us with one really fascinating question to ponder. As our data gets bigger and our tools get smarter, what hidden, world-changing rhythm are we going to discover next?